And I'm going to talk about a different method for doing test hypothesis. It is known as the p-value method. So p-value is a probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. So we're assuming the null hypothesis to be true when this occurs. So we've got three different possibilities. We have a left tail example where we've got the area here, this is alpha, on the left region. So the p-value is the area from the test statistic to the left. So if we have a test statistic that is, say here, where this x is, so this is our test stat, the p-value is the area from the test stat to the left. Now in this case, we know that we would fail to reject because it's not in that critical region. However, if it were in the critical region, we would reject. So essentially, since that level there is alpha, our rule is if the p-value is less than or equal to alpha, we reject the null hypothesis. And thus, if it is greater than alpha, if the p-value is greater than alpha, we fail to reject. So this p-value, it's an area that would be larger than our level of alpha. Our second option is a right-tailed test. We learned about that. Right-tailed test, this is left tail. Let's make a right-tailed test. We'll do that in a different color. That means our alternative hypothesis will be the mean or proportion, whichever, because this works for both types, is strictly greater than some value. So in this case, our entire level of alpha is on the right side, and the p-value is the distance from the test statistic. So say this is the test stat here. Then the p-value would be the orange region there, which is smaller than our level of alpha, which would mean we would reject. Again, we know that to be the case, given the fact that it's in the critical region. But the area, and you can find the area in a z-distribution using the normal CDF. However, our calculator is going to do it all for us, and I'll go over that with an example in just a moment. I'm going to scroll down a little bit here and talk about the two-tailed variety. So if we have two-tailed, we take twice the area in the tail beyond where the test statistic is. So essentially, say we have an area where we have alpha over 2 here and alpha over 2 here, where we're splitting up our alpha for a two-tailed test. Then whichever tail we're by, and we'll set this here with our mu sub naught or p sub naught, whichever we're looking at here, whether it's a mean or a proportion. And whichever side of that center we have, say our test statistic is over here, then we look at the area towards the tail it's on. This happens to be on the right tail, so we're going to figure out that area and then double it. And that will be our p-value. So let's try an example here where the calculator is going to just show us how to do it. All right, so this says the CDC reported on trends in weight, height and body mass index from the 1960s through 2002. It says the general trend was that Americans were much heavier and slightly taller in 2002 as compared to 1960. Both men and women gained approximately 24 pounds on average between those years. So then we have in 2002, the mean weight for men was reported as 191 pounds. And this is in 2002. Suppose that an investigator hypothesizes that the weights are even higher in 2006, indicating that the trend will continue over the next 4 years. So we essentially want to do this. They're looking for increase, so the alternative, HA, is going to be the mean is greater than that value back in 2002, so the mean will be greater than 191. Our null will be that the mean is 191. All right, so we're given the set of summary stats here. So they ran in 2006. Suppose we have resources available to recruit N is 100 men into the sample. We weigh each participant and compute summary statistics on the sample data. Suppose that the sample, suppose in the sample we determine the following. So we have these three summary stats. N is 100. Our sample mean X bar is 197.1. And our standard deviation S for the sample is 25.6. We want to test this. Well, let's write down the other information that we know. We have the null and alternative hypothesis. What test in the calculator do we want to run? Well, first, what type is it? We're dealing with a mean. Therefore, this is quantitative. So then we need to ask ourselves a question. Is N 30 or more? Well, N is 100, which is at least 30, so we can use a large sample test. So this is going to be a z-test. And how do we get a z-test? Well, in the calculator, we're going to type in, it's going to be very similar to the confidence intervals. It is going to be stat tests and then just z-test. So the z indicates we're going to use a z version. We'd use a t if we had a small sample in a normal distribution or something approximately normal. We are doing a test of hypothesis, so that's where we get z and test. All right, so let's go to the calculator. Stat, go over to tests. It happens to be the very first option, number 1 there. We don't have data, we have summary stats. So we're going to need to arrow over to stats and hit enter. So mu sub naught, remember mu sub naught is what we're trying to test. The mu sub naught here is 191. The standard deviation, well, we don't have sigma, but we have S, which is 25.6. If we knew what sigma is, we would simply put it in there. X bar is given as 197.1. And I wrote a 7, so let's change that to a 1. And finally, we need N, which is 100. All right, so all of that is good, and that's going to do any of the 3 different types of tests, whether it's two-tailed, left-tailed, or right-tailed. We will get the same test statistic regardless of our next choice, but this next choice is very important for the p-value. We have to tell it which version this is. Well, we're looking at greater than, so the arrow points to the right, so we're going to choose the greater than option, which is actually already chosen. So that's the test we're going to run. We're going to get a completely different p-value if we don't choose that one. So let's go to calculate, and we'll write down some stuff that we have. All right, we are told that RZ is 2.38. Well, We know what that's going to relate to as far as a critical value, but let's take a look at the p-value. And we only have one thing that's p here, and it's under the z, this 0.0086. So p is the p-value. That's 0.0086. That's the area from our test statistic to the right. How does that compare to alpha? Well, this is alpha here, right? So this means alpha is 0.05. How does this relate to alpha? That's less than or equal to 0.05, which is alpha. And from our conclusions as before, this means we reject the null hypothesis.